Thanks a lot. The organizers suggested that I inflict this on you, and it's actually quite difficult in a sense because after Max Di Ventra's talk this morning and the coming talk of Fabio Traversa later, then I'm kind of humbled in a way. Admittedly, I haven't heard Max Di Ventra's talk because I was lecturing, but still. So I'm going to talk about quantum membristors in that we are proposing a mechanism to actually build, well, from an experimentalist point of view, this is a tall order, but we are proposing an idea that could implement quantum mechanically a membristor. So this is based on a paper we published some time ago with Paul Pfeiffer, Max Di Ventra, Miquel Sanz, and Quique Solano. I will start by doing a summary of basic concepts. I will go very fast through these, essentially because Max has already told you something about universal MEM computing. And then I will try to convince you that it is sensible and feasible to think of a quantum membristor, and that this will provide us with new tools in the general context of quantum information. So, coming to the review, I will simply remind you that classical membristors were described as by these first-order equations in which you have, this is in particular a potential-driven membristor, in which the conductance is a function of a state variable which evolves in time in this dynamical system. And actually, this is, as you can see, actually from a paper by Max Di Ventra, Pershin, and Leo Chua, who proposed the membristor concept. One of the characteristic things of an ideal membristor is that they have this pinched hysteresis loop. I do put this up again because it will come up in our presentation of the quantum membristor. This loop, this hysteretic loop, is pinched in the ideal case, because essentially when the potential is zero, the intensity is zero, and the area is frequency dependent for harmonic driving, and in a sense, it does measure memory. General MEM elements will be described in this way, where U is the driving element of the system. In the previous case, that was the potential, and EX is a state which can be a multi-variable. And there is a generalized conductance, if you will, or resistance, or whatever the case might be, and the state variable is going to obey some dynamical equation. This is important and relevant whenever you speak about neuromorphic or neuro-inspired or biomimetic computing, in that when you come to look at the Hodgkin-Huxley model for the giant axon of the squid, one is going to come up, one is going to find that there are membristors in this system. In a nutshell, for all of us that know nothing about biology or almost next to nothing to biology, when one has a neuron, the neuron is going to connect via an axon, and then these connections and these synaptic connections to other neurons or to other places where the action potential is going to act by this action, and in the action there are going to be generally some channels for ions, in particular potassium, sodium, calcium, different ions. In a myelinated axon, it will be at the nose of Ranvier that these are going to be placed. The actual case that they looked was not myelinated, but still you have this kind of object. And what this model pretends to do is to describe how action potentials are fired and then propagated along the axon. Essentially, it's the propagation of the action potential along the axon. And they did this by actually using this particular animal model because it has a huge diameter. It's almost 1 millimeter in diameter. So they could actually put in measuring apparatus, electrode clamps in the axon. And this is the equivalent circuit that they came up with, where these are memristors. So essentially, you have some general capacity. This is the potential. And this, the conductance of this potassium channel is going to be membristive conductance. Similarly for the same channel, and this is what is called the leakage. And these are the equations. So they are tiny in a way, but essentially, as you can see, this M inverse and M inverse for sodium and potassium, they are actually the conductances for the corresponding channels. And you can see that they are controlled by some state variables which obey some differential equations. So this is actually precisely the membristor which was proposed by Liu Chua. So this is why we say that whenever we're looking at neuromorphic or neuron-inspired computation, one should be looking for this kind of object, at least when it comes to the propagation of the action potential in the neuron. Sorry, I don't know why I went backwards. Sorry about that. This is essentially something that perhaps with a different graph, but Max has surely been talking about this morning, in that there can be universal memory computing machines in that you change the von Neumann architecture to a different kind of architecture in which the computational memory is computational and memory at the same time. Perhaps, as he is advocating, this change in model will help us in compute many different ways or in a faster way, and this is their formalization taken from the paper by Max and Fabio some time back. Now to the quantum membristor itself. If we want to do neuromorphic quantum computing, if we want to be inspired by the way that the brain works or that life works in quantum computing, there are a number of things that one has to address. Because the fact is that these machines, they are channels where you add input signals and propagate it to a different place, and they have some memory of how they have been activated. So we would need this kind of adding inputs, we would need memory, and those are things that seem hard to do in a quantum context, seem to be forbidden in particular. Of course, there is something like the quantum adder, or Viper, which is possible, as was proved by Unai here in Kike's group some time back, in some sense, and other people. And now then we have what about memory? So what we propose is let's look at the quantization of this circuit. In particular, let's look at the quantization of the membristor, in which case we will have some systems with memory in which we have a quantum description. In general, for quantum mem devices, well, the general idea is if you give me a Lagrangian, I am a theoretician, so for me, a Lagrangian is, you can quantize it. You do canonical quantization, okay, it might be hard, I might have to go through some hoops to do it, but that's it. Give me a Lagrangian, and that's it, essentially. And that was actually done by Max with Yuri Pershin and Guy Cohen some time back. But the membristor has some subtleties in that, obviously, it is a dissipative device. Since it is dissipative, it can be described by a Rayleigh function, for instance, or some dissipative function, but it cannot really be quantized properly. So the question is, what does happen when we couple a membristor to a superconducting circuit? So the idea is, what happens if one plugs it in? Now, as you all know, quantum mechanics implies unitary evolution for isolated systems, so there is no intrinsic memory to talk about. So what we propose as a technique to describe a quantum membristor is to do quantum non-Markovian process engineering. This is we're going to do one particular engineering of a quantum non-Markovian process. And this is going to happen by having a dissipative environment, as is known, and we will have weak measurement of a circuit variable. We're going to put a circuit variable here. We're going to make some weak measurement of that quantity. And then we propose that there be a classical feedback controlling the dissipative environment. This is our idea. This is how we propose to implement a quantum memristor. The dissipative part, this is very well known because, as you know, if I have a constant resistance, then the real part of the admittance is going to be a constant for all omega. So the idea is, okay, I have some oscillator, and then I put in some other oscillators. To each oscillator, I will have some contribution at a particular frequency. And then if I add them all up, then I will have an effective resistance. And this is nothing but Caldera-Leggett. So what we suggest is that we have this dissipative element in a similar way, and that we can move the height of this resistance by performing weak measurements and then doing classical feedback on this part. So we did look at memristor in this, with this idea coupled to an LC circuit. And the way we did it was by looking at the stochastic master equation, in which we are looking at a density matrix where we have the free part, and then we have this interaction term, this bus, and then we have the measurement. We are going to do weak measurements, so we have to use a formalist for weak measurements. And this is associated with the weak measurement itself that's going to evolve according to this law. So this is the density matrix for the oscillator part that we look at. This is the specific form that we took in order to do this computation. This is the stochastic part of the measurement, the deterministic part of the measurement, the coupling, and with the usual approximations. So it is a set of nonlinear coupled stochastic differential equations of the Caldera-Leggett type. This was implemented on the machine for a particular situation, and then we had different runs of it, different numerical simulations, and for some particular values, we did one thing. What we wanted to check is whether this indeed can describe a quantum memristor. So we wanted to see if we could recover something that is known of a classical memristor, which is the hysteretic loop. So what was done here is we charged our system with a current and then let go. And we did that for many realizations. And then we averaged over all these realizations. And the result after this averaging was this. It was charged with coherent state, so it was fairly classical. So the initial state was fairly classical, and this allowed us to simply compute a Gaussian evolution, and therefore we could have sensible control of the numerics. And what happens is indeed that we have this hysteretic loop that's going to decrease essentially because this is dissipative. We have charged it. It's not driven. It's not a driven system. It is charged and then it let go. So therefore we have dissipation. But we do have the form of the hysteresis loop, which is going to start closing, is actually of the form that was desired. So indeed, we claim, and this is our main claim, that we have indeed proposed a quantum system or a quantum set of equations that do describe in the proper classical limit a classical memristor. And this is why we claim that this is indeed a quantum memristor. There have been several proposals of how to implement this, because what we have provided here is a protocol, simply a protocol to engineer membristive behaviors in different quantum platforms. So Mikkel in particular has been very active in excuse me, in proposing implementations in different concepts. In particular, there is a proposal for an implementation in photonics, fairly recent, by Mikkel Sanz, Lucas Lamata, and Quique Solano. And also there is a previous proposal of superconducting circuits, which was by Juha Salmiletto, Frank here, Frank Deppe, Max de Ventra, Miquel Sanz, and Quique Solano. So let's see if this happens. In particular, this implementation in supersymmetric circuits was by via of an asymmetric squid. You can find the details in the paper. And then what was done, it was the quantum squid neuron. As I told you, the Hodgkin-Huxley model was actually for the giant axon of the squid. So in particular, you can check the poster by Tasio, where he's proposing a quantum version of the Hodgkin-Huxley model for this axon, for the giant axon. So as you can see, we are exploring the possibilities of this quantization of MEMRISTOR. We do know that this system, with this feedback, weak measurement and classical feedback, does have the proper behavior in the classical limit. And we haven't really explored all the possible different quantum regimes that it might obey. But we have definitely proposed possible implementations for it. And with that, I think I have been really, well, it's been much shorter than expected. But I'm game for questions.
Plenty of time for questions. Here.
Oui.
So you showed very beautifully that with the coherent states, you went back to the classical limit.
Yeah.
You just said you hadn't done it, but what's your expectation as to what will happen if the input was a Fock state in this system?
If it was offset, you mean?
A Fock state.
A Fock state.
Yeah.
Remember, this is, yeah, we would have to perform the averages. That's why. It wouldn't be as neat, but we would definitely find that it would have to dissipate.
Yeah.
It would have to go to the vacuum for sure. But the shape might be radically different at the beginning of the evolution, and then it would classicalize, apart from everything else, because we are doing measurements as well. So
yeah.
we're dissipating and measuring. So
it's
that
going
would be
to head
expected
towards coherent as that continues.
Yes, for sure. But the speed of the coherence, that is something we have not. I don't think we have really explored. And that's so we know there's going to be coherence. We know that it's going to classicalize in this sense, but we don't really have any grasp as to the speed of the decoherence. We didn't do a proper exploration of the parameter space, because there are, as you can see, there are plenty of parameters in this circuit, in this proposal. Excuse me. I hate these machines. It always happens whenever you want to get somewhere fast.
It's all right. We have 15 minutes for question time. We've got.
Well, I didn't want to impose on you too much, actually. Sucks. So as you can see here, we have essentially this temperature, the bath situation. We have the coupling. We have this K state, and then we have the parameters of the state itself.
Yeah.
So and remember, we have to choose some form for lambda, essentially. So the space of parameters is not very clear, and we really wanted to have more of a handle of how these things look in a particular implementation before doing an exploration of all those. But the proper answer to your question is, it will classicalize, it will decohere. We don't know how fast.
Okay, thank you.
Kike, you want to do it?
Andrew, you should have asked this before to think it better, because it's a very irrelevant question, in my opinion, the story of the input. The goal was just to see the semi-classical limit just to see, of course, something that can be called hysteretic. But in fact, the set of equations becomes messy with the Fock state as an input, and in fact, this is just ongoing work. And I am sure you were thinking in your device, what happens if I create an optical MEMRISTOR and I provide a photon? And that's pretty interesting question that we don't have the full answer, but that's something that we can work out, in fact.
Miguel is scratching his head right now, actually.
It's Miguel that gave me the answer, it's not mine.
So any other questions? So actually, I have also a question. So for example, you were mentioning that you wanted to capture some of the classical MEMRISTOR features, like, but do you have an intuition of how different it can be, or actually maybe, yeah. So.
Oops. Oh.